Wasn't lying to you. Shown in the diagram below are two plates which are 1.2 meters apart from each other vertically and have an area of 1.4 square meters. Contained within the boundary of the plates is a fluid where the coefficient of viscosity is 25 Pascal seconds. The upper plate is attached to a string which goes over a smooth pulley to a block of mass 4. Find the shear stress once the block has moved a distance equivalent to the height between the plates. There's a lot of words in there, so I recommend just going ahead and sort of making sure that you understand the problem, and when you're ready, you can come back for the solution. So I'll just try recreate the diagram, because I did these ages and ages ago, so the way I do things is different, obviously because I have a new device. So this has a mass of 4. This cross-sectional area is one, or not cross-sectional, but the actual area of the plate is 1.4, and then the distance between them vertically is 1.2. So the first thing we have to do is find. So we're looking for tau. So tau is eta times delta v over delta x. I hate these fucking dots that appear all over the place. So we're given eta. We know eta is 25, and then we're looking for delta v over delta x. Now, delta x we can infer from the question is 1.2, and all we're looking for is delta v. So delta v we can think is this. Now, the plates we'll consider as massless. This will have downwards 4g and, well, tension we're actually excluding as well. The tension you can actually consider as part of the shear force, but the shear force is actually the plates themselves, not any sort of exterior forces acting on it. So we know that that's the weight force, and that's equal to 4 times a, so the acceleration is just g. Next, we'll form a CVAT table. So what we're looking for is the final velocity. We'll say that it starts from rest, 1.2 meters, and acceleration g. So we're going to use v squared is u squared plus 2as. So filling all that in, 2 squared plus 2g times 1.2. Look at the square root, we get 4.8 meters per second, which is actually handy enough. So if we go here, we get tau is 25 times 4.8 over 1.2. 48 over 12 is 4, and so the shear stress is 100. Now, the units of shear are not actually newtons. If we think newton meters squared, we'll have a spare per second, so we'll have newton meter squared seconds. What we actually have for the shear stress is actually a shear pressure force of 100 newtons per meter squared, or 100 pascals, or however you want to say it. The numerical answer for this is tau is 100 no matter what.